Climate change is often discussed in terms of politics, economics, or weather, but at its core, it is a chemical story. The warming of the planet is driven not by abstract ideas, but by specific molecules in the atmosphere interacting with energy in precise, measurable ways. Climate chemistry explains why changing the composition of the air changes the temperature of the Earth itself. This is the Learning Studio, where chemistry is explained as the hidden engine behind global systems. And after understanding how environmental chemistry governs pollution in air and water, the next step is to understand how atmospheric chemistry operates on a planetary scale, influencing climate, ecosystems, and human survival. Most people think climate change is simply about rising temperatures, but in reality, it begins with how certain gases interact with infrared radiation. For example, when sunlight reaches Earth, the planet absorbs energy and re-emits it as heat. Gases like carbon dioxide, methane, and water vapor absorb some of this outgoing heat and re-radiate it back toward the surface. This process, known as the greenhouse effect, is entirely chemical in nature. At the molecular level, the mechanism is precise. Greenhouse gas molecules vibrate when they absorb infrared radiation. These vibrations store energy temporarily and then release it in all directions, including back toward Earth's surface. Increasing the concentration of these gases increases the amount of energy trapped in the atmosphere, shifting the planet's energy balance and raising global temperatures. This chemical understanding was first quantified by Svante Arrhenius, who calculated how changes in carbon dioxide levels could alter Earth's temperature. Decades later, Charles David Keeling provided direct evidence by measuring rising CO2 concentrations in the atmosphere with extraordinary precision. His data revealed that human activity was chemically altering the composition of the air on a global scale. Climate chemistry also explains feedback loops that amplify change. Warmer temperatures increase water vapor in the air, which traps more heat. Melting ice reduces reflectivity, allowing Earth to absorb more solar energy. Chemical reactions in oceans change how much carbon dioxide they can absorb, linking atmospheric chemistry directly to ocean chemistry and ecosystems. These processes affect far more than temperature alone. Changes in atmospheric chemistry alter rainfall patterns, intensify storms, disrupt ecosystems, and acidify oceans. The chemistry of carbon, nitrogen, and sulfur cycles connects climate change to agriculture, biodiversity, and human health, showing that climate is not a separate system, but an integrated chemical network. Understanding climate change as a chemical process transforms the conversation. It becomes measurable, predictable, and actionable. Emissions are no longer abstract numbers, they are molecular inputs. Mitigation strategies become chemical solutions, such as reducing reactive gases, developing alternative energy pathways, and enhancing natural carbon sinks. And once we understand how atmospheric chemistry drives climate change, the next question naturally follows. If chemistry helped create this crisis, then how can chemistry help solve it through energy transformation and sustainable systems? That question takes us directly into the next episode, where we explore energy chemistry, fuel cells, hydrogen, and the chemistry behind clean energy transitions.